Hi, my name is Nick Jackson. I'm a professor of chemistry at UIUC. And what I'm going to talk to you about today is how you actually turn a molecule into something that a machine learning algorithm can use. So, we have on the left here a molecular structure, some arbitrary molecular structure. And I want to take this structure and I want to feed it into some statistical machine learning algorithm that will make a prediction on a property. So, in comes the molecule, some black box machine learning algorithm acts on it, and it predicts a physical property like solubility, melting point, toxicity, optical gap, anything you might be interested in. Now, one challenge with this is that you need a your machine learning algorithm needs basically a numerical format to act on, right? Computers, naively speaking, use numerical vectors to do their mathematics. And so what you need to be able to do is convert your molecular structure into a numerical vector, into a list of numbers that an algorithm can operate on. This task is incredibly important in the machine learning pipeline because how you turn a molecule into a vector or into a list of numbers that a computer can act on determines how effective your prediction algorithm can actually be. So this process is referred to as molecular featurization. That is the fancy phrase for it. But molecular featurization just means how you turn a molecular structure into numerical data that a machine learning algorithm can use. So the easiest way to do this is to describe your molecule by a list of numbers. You usually refer to this list of numbers as an array or a vector. And all that means is it means that it's a list that stores a bunch of numbers in it. So if I have this molecule, at the end of the day, I'd like to have a list of numbers, for example, some random numbers I drew here, that characterizes that molecule hopefully uniquely. And so the question is, how do I generate a list of numbers for a given molecule? This process called molecular featurization is entirely human-driven for most machine learning applications. One of the big advances of modern machine learning is that neural networks and deep learning can try to figure out these featurizations on their own. But in the majority of cases, there's a human behind the scene who's dictating how you convert a molecule into a numerical vector that a computer can work with. So if I want to turn this molecule up here on the left into a list of numbers, let's say 3 numbers, one way I could do it is I could say, well, the identity of this molecule can be represented as numbers, where I would say, OK, a certain slot is how many oxygen atoms the molecule has. Another slot is how many double bonds it has. And another slot is how many 6-membered rings that molecule has. So if I look at this structure up here on the left, I see 1, 2, 3, 4, 5, 6, 7 oxygen atoms. So I would put a 7 here. I see 1, 2 double bonds, so I would put 2 there. And I see 1 6-membered ring, so I would have a 1 there. As simple as this sounds, this is the process of turning your molecule into a numerical vector that a machine learning algorithm can read. And so what you're probably wondering is, OK, how do you pick these descriptors that featurize your molecule? How do you make sure they're complete? And this is, again, a process that is entirely human-driven. So you could list out many other properties. You could list out as well how many carbon atoms are in the molecule, what the size of the molecule is in distance. You could list out how many sp2 carbons or sp3 carbons there are. You can basically do this as far out as you want. So what I wanted to show here is, if I were to just go by this, say, 3-feature descriptor of a molecule, now I can say, OK, here are 3 molecules. They all look different. And the point of featurization is that I make a numerical vector that can characterize different molecules so that my machine learning algorithm can see different structures. So I have beta-carotene, quercetin, and an anthocyanin molecule. These are all basically antioxidants that you'll find in fruits and vegetables. And now I want to turn these each into numerical vectors. So using the description above, or the prescription above, I can have beta-carotene described by 0, 11, 2. There's a lot of double bonds and there's no oxygens. There's 2 rings. Quercetin by 7, 8, 3, and an anthocyanin molecule by 6, 9, 3. So here are numerical vectors that are characterizing each of these three molecules. And of course, as I said before, these aren't every possible characterization of a molecule you want, but the process of assembling these vectors as for what you think is important in a molecule is integral to the performance of any machine learning algorithm. So there's nothing stopping you from making longer and longer vectors that you think are important to describing the properties of your molecule. There are some numerical reasons why you don't want to have something really, really, really long, but in principle, it's entirely up to the user. So one thing that's really cool about turning molecules into numerical vectors is that it lets you quantify the similarity between molecules. So if I look at these three molecules on the left, I naively say, okay, the bottom two, quercetin and anthocyanine, are obviously more similar than beta-carotene. But I'd like to be able to quantify that numerically. And so since you can write these two molecules as these three-dimensional vectors, these lists of three numbers, you can use an analogous computation as you would to compute, say, the distance between 2 points. Right? Hypothetically, you could be like, okay, this is kind of like if that's an x, y, z, and this is an x, y, z. And so then I know that if I want to calculate the distance between 2 points, I can use an analogous calculation that would be like the distance is equal to x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And that would be a distance between 2 points in this space. So if I do this calculation explicitly for these three-dimensional vectors, and I do it for quercetin, beta-carotene, I would get 7.68. And I do it for quercetin and anthocyanin, I would get 1.41. This says that the distance between these two molecules, 1.41, is smaller than the distance between these two molecules, which is 7.68. So this is actually a way to not only just characterize a molecule for a machine learning algorithm to read, but to actually start to quantify numerically how similar or dissimilar molecules are, which is pretty cool. So I hope this gives you a brief idea of how you can turn molecules into the formats that are needed for machine learning. It's a human-driven process, so you just need to take a list of numbers that describe your molecule and turn it into a vector or a numerical array, which is, of course, strongly informed by the human choice of what should matter. And if you do this, it has the cool feature that you can quantify how similar different molecules are to each other by treating them as these vectors.